Here we are going to discuss about inverse set transforms. In the previous video we have gone through set transforms. So it is better to remember the set transform pairs because it will be useful for finding the inverse set transforms. So mainly two methods are used for finding the inverse set transforms. First method is partial fraction expansion method and the second one is power series expansion method. In the case of partial fraction expansion method, first of all, we will find the partial fraction expansion of the given series. Then we can easily find the inverse set transform. So let us see. F of k is a discrete sequence. Then f of z is given by the set transform f of k. Okay. So in the question we will be given by the set transform pair, that is f of z. You are given with the f of z. So let us, this f of z is in the form of a p by q form, that is given in this, that is b0 z raised to m plus b1 z raised to m minus 1 plus etc. divided by z raised to n plus, that is it is in the form of p by q. Okay. Here whenever m less than or equal to n, that is the condition we are taking. In this case we can represent this f of z in this form, that is a0 plus sigma I equal to 1 to n ai by z plus pi. That means when we are getting this form in this form, see, we can easily find the inverse set transform. Here a0 is a constant, a1 a2 etc. up to an are the residues, and p1 p2 etc. up to pn are the poles. And also in some cases it is better to express this formula or this one in the form of f of z by z. Then you can easily find the z transform. See here, whenever m equal to n, you have to divide the numerator by this denominator polynomial. Then you will be getting a0 term here. Okay. If m less than or equal to n, you will be getting this term alone. Okay. So this will be easier when you are doing a problem. So in this cases there are different chances such that the poles or the roots are the real and distinct functions. See here pole is pi, and here when we are factorizing this f of z in this form, there are different chances that we are analyzing in case 1, case 2 and case 3. That means pi may be real and distinct, it may be complex conjugate pair, or it may have multiple values. Okay, so first case is when the roots are real and distinct. In that case we can represent this f of z in this form. That means a0 plus a sigma, we have the second term is this one, right? And this will be in the form of this. That means here p1 p2 etc. up to pn are distinct. In that case we can easily represent a f of t in from the we will easily get f of t from f of z. Okay, so in that case, first of all we want to find a1 a2 etc. up to an, and the equation for finding this one is a1 is obtained by multiplying f of z by z plus p1, and we have to put the value z equal to p1, z equal to minus p1. So the general equation is that a will be equal to z plus pi into f of z at z equal to minus pi. Similarly, if the roots have multiple values, that means z plus pi is repeating more than once, then what will be the form? See here f of z is in the same form. See a0 plus a1 by z plus p1, a2 by z plus p2, and it will goes up to n terms. Suppose if any of the pole is repeated multiple times, that means z plus px is multiple times, that means z plus px all raised to q is there, that means px root is repeating. So in that case we want to find how can we find this quotient, that is ax0. So that has an equation, that is ax r can be find out in this way, 1 by r factorial into dr by dz r z plus px all raised to q into f of z, where z equal to minus px. See here we are utilizing the derivative term, and we will be derivating r times. How many times these roots are repeating, that much times we are taking this derivative. And again similar equation, that is if we are considering z plus px all raised to q term, then we have to multiply this f of z with z plus px all raised to q, and we have to put z equal to minus px. The only difference is that here we are taking derivative, that is 1 by r factorial into dr by dz raised to r. Next case is complex conjugate pole. Here also f of z is in the same form, and we are representing this like this. See here you can see this root is complex conjugate. So we can represent ax by z plus sigma plus j omega plus ax conjugate. That is here the root is sigma plus j omega, here it is sigma minus j omega. That is the difference. Okay. So these are complex conjugate pairs. In that case, how can we find out this coefficient? So that is also an equation. That means here ax is obtained in the same manner as we have discussed in the first case, that is this one. So there is no difference, and ax conjugate is the conjugate of this one ax. Okay, that means the residue ax is evaluated as in the case of case 1, and the residue ax conjugate is the conjugate of ax. So there is no difference in the case of complex conjugate pair. Only thing is the poles will be complex conjugate. That's the difference. Okay, the difference is for calculating in the case of roots having multiple poles. Okay. So there is another method also for finding the inverse set transform, that is power series expansion method. In that case we have f of k is a discrete series. We will be given with f of z, that will be the set transform f of k. Okay. So by the definition f of z, that is for the set transform definition, sigma k equal to minus infinity to plus infinity f of k into z raised to minus k, and here this will be f of z. So we will be given by f of z. So we can represent that f of z in terms of, see, when you are putting different values for k, you will be getting f of 0 z raised to 0, and positive terms are f of 1 z raised to minus 1, etc. Similarly, we will be getting negative terms like this. So from this expansion, you can easily find the inverse set transform. So let us do some problems, then this theory portions will be clear. So first of all, find the inverse set transform of f of z is equal to this form. So you are given the set transform, so you have to find the inverse set transform f of k. Okay. So first of all, you have to take this form. Okay. Here you can represent this f of z. It is better to represent this f of z in the form of f of z by z. So first of all, when you are looking at the denominator side, you can rearrange this as c 1 by 1 minus 1.5 into 1 z inverse means 1 by z. So you can write it as 1.5 by z plus 0.5 z raised to minus 2 means 0.5 by z square. Okay. So you can multiply the denominator terms and you can rearrange this equation. So you will be getting z square. You can multiply z square with this, so z square minus 1.5 z plus 0.5, and denominator z square will come to numerator, so z square. So here the denominator side can be expressed as, see, it can be expressed as z minus 1 into z minus 0.5. That is a simple root finding method. So this will be in this form. So you can easily also you can find that here it is better to represent as it is in the form of f of z by z. So once z is taken to left side, so it will be equal to f of z by z, that will be equal to z divided by z minus 1 into z minus 0.5. So this term here m is less than, here m is 1 and n is 2. So m is less than n. So here you can represent it in the partial fraction method. So f of z by z can be expressed as a1 by z minus 1 plus a2 by z minus 0.5. Here you want to find a1 and a2. Here the roots are distinct. One root is 1, other one is 0.5. So you can easily find a1 and a2. A1 equation is f of z by z into z minus 1 at z equal to 1. Okay. So when you are substituting that values of f of z by z, then what is f of z by z? F of z by z is this. Okay. This into this quantity and put z equal to 1. So you will be getting a equal to a1 equal to 2. Similarly, a2 can be found out by f of z by z into z minus 0.5, putting z is equal to 0.5. So you will be getting a2 equal to minus 1. So you can substitute that values in this equation. So f of z by z equal to 2 by z minus 1 minus 1 by z minus 0.5. Next you can rearrange it in the form f of z equal to, z can be taken to right side. So this is the form. So you can see that this is familiar to you. So f of k can be, that is inverse set transform, can be found out from the f of z by using the set transform pairs. Here you can see that 2 is a constant. When you are putting 2 somewhere when you are keeping 2 there, you can find that z by z minus 1. You are familiar with Z by Z minus 1. What is the inverse Z transform of this pair? You know that if we are taking the step function u of k, you may remember that its in Z transform is Z by Z minus 1. So this represents the u of k. Okay, so you can put 2 into u of k. Okay, so that is the first term. And next thing is, this is in the form of Z by Z minus a. So you may remember the Z transform pairs. Z by Z minus a constitute that a raised to k. That is, whenever f of k is a raised to k, its Z transform is Z by Z minus a. So this is the way you have to do the problem. So it is better to remember the Z transform pairs. Okay, so Z divided by Z minus 0.5 points to 0.5 all raised to k for k greater than or equal to 0. So this is the inverse Z transform of f of Z. So this is the way you have to do the problem. Here we have discussed about roots are distinct and real cases. Similarly, we will be coming across roots with multiple poles, and sometimes the roots may be complex conjugate. In that case also you can do the same procedure. And we have given the procedure in the case of 3 cases. Okay, that's all about this topic. Thank you.